What is the Muon puzzle and why is its solution important to science? What is the uniqueness of the Moscow Engineering Physics Institute research and what challenges does it face? Stay tuned to the Russian House podcast to know more.
A muon is an elementary particle similar to the electron with an electric charge of -1 electron and a spin of 1/2, but with a much greater mass. It is classified as a lepton. As with other leptons, the muon is not known to have any substructure. That is, it is not thought to be composed of any simpler particles. The muon is an unstable subatomic particle with a mean life of 2.2 microseconds, much longer than many other subatomic particles. As with the decay of non-elementary neutron, muon decay is slow because the decay is mediated only by the weak interaction rather than the more powerful strong interaction of electromagnetic interaction, and because the mass difference between the muon and the set of its decay products is small, providing few kinetic degrees of freedom for decay. Muon decay almost always produces at least 3 particles, which must include an electron of the same charge as the muon and 2 types of neutrinos. Like all elementary particles, the muon has a corresponding antiparticle of opposite charge, +1 electron, but equal mass and spin. The anti-muon, also called a positive muon. Muons are denoted by the letter mu with a minus, and anti-muons by a mu with a plus. Formerly, muons were called mu mesons, but are not classified as mesons by modern particle physicists, and that name is no longer used by the physics community. Due to the great mass, muons accelerate slowly than electrons in electromagnetic fields and emit less deceleration radiation. This allows muons of a given energy to penetrate far deeper into matter because the deceleration of electrons and muons is primarily due to energy loss by the mechanism. For example, so-called secondary muons created by cosmic rays hitting the atmosphere can penetrate the atmosphere and reach Earth's surface and even into deep mines. Because muons have a greater mass and energy than the decay energy of radioactivity, they are not produced by radioactive decay. However, they are produced in great amount in high-energy interactions in normal matter, in certain particle accelerator experiments with hadrons, and in cosmic ray radiation with matter. These interactions usually produce pi mesons initially, which almost always decay to muons. As with other charged leptons, the muon has an associated muon neutrino, which differs from the electron neutrino and participates in different nuclear reactions. Muons were discovered in 1936 while studying cosmic radiation. Dr. Anderson noticed particles that curve differently from electrons and other known particles when passed through a magnetic field. They were negatively charged but curved less sharply than electrons, but more sharply than protons for particles in the same velocity. It was assumed that the magnitude of their negative electric charge was equal to that of the electrons, and so to account for the difference in curvature, it was supposed that their mass was greater than an electron, but smaller than a proton. Thus, Anderson initially called the new particle a mesotron, adopting the prefix meso from the Greek word for mid. The existence of the muon was confirmed in 1937. A particle with the mass of the meson range had been predicted before the discovery of any mesons by a theorist from Japan, Dr. Yukawa. Because of the mass, the mu mesons was initially thought to be Yukawa's particle, and some scientists originally named it the Yukon. Yukawa's predicted particle, the pi meson, was finally identified in 1937, again from cosmic ray interactions, and was known to differ from the mu meson by having the property of a particle that mediated the nuclear force. With two particles now known with the intermediate mass, the more general term meson was adopted to refer to any such particle within the correct mass range between the electron and nucleon. Further, in order to differentiate between the two different types of mesons, after the second meson was discovered, the initial meson-trap particle was named the mu meson. As more types of mesons were discovered in accelerated experiments later, it was eventually found that the mu meson significantly differed not only from the pi meson, but also from all other types of mesons. The difference, in part, was that mu mesons did not interact with the nuclear force, as pi mesons did, and were required to do. Newer mesons also showed evidence of behaving like the pi meson in nuclear interaction, but not like the mu meson. Also, the mu meson's decay products included both a neutrino and an antineutrino, rather than just one or the other, as was observed in the decay of other charged mesons. Muons arriving on the Earth's surface are created indirectly as decay products of collisions of cosmic rays with particles of the Earth's atmosphere. When a cosmic ray proton impacts atomic nuclei in the upper atmosphere, pions are created. These decay within a relatively short distance, meters, into muons, the preferred decay product, and muon neutrinos. The muons from these high-energy cosmic rays generally continue in about the same direction as the original proton, at a velocity near the speed of light. Although their lifetime without relativistic effect would allow a half-survival distance of only about 456 meters at most, flight to the Earth's surface, since in the Earth's frame the muons have a longer half-life due to their velocity. From the viewpoint of the muon, on the other hand, it is the length contraction effect of special relativity that allows this penetration, since in the muon frame its lifetime is unaffected, but the length contraction causes distances through the atmosphere and Earth to be far shorter than these distances in the Earth rest frame. Both effects are equally valid ways of explaining the fast muons' unusual survival over distances. Since muons are unusually penetrative of ordinary matter, like neutrons, they're also detectable deep underground, 700 meters up to, and underwater, where they form a major part of the natural background ionizing radiation. Like cosmic rays, as noted, the secondary muon radiation is also directional. Muons are unstable elementary particles and are heavier than electrons and neutrinos, but lighter than all other matter particles. They decay via the weak interaction because leptonic family numbers are conserved in the absence of an extremely unlikely immediate neutrino oscillation. One of the products, neutrinos of muon decay, must be a muon-type neutrino, and the other an electron-type antineutrino. Because charge must be conserved, one of the products of muon decay is always an electron of the same charge as the muon, a positron if it is a positive muon. Thus, all muons decay to at least an electron and two neutrinos. Sometimes, besides these necessary products, additional other particles that have no net charge and spin of zero are produced. Negative muons can form muonic atoms by replacing an electron in ordinary atoms. Muonic hydrogen atoms are much smaller than typical hydrogen atoms because the much larger mass of the muon gives it a much more localized ground state wave function that is observed in the electron. In multi-electron atoms, when only one of the electrons is replaced by a muon, the size of the atom continues to be determined by the other electron, and the atomic size is nearly unchanged. However, in such cases, the orbital of the muon continues to be smaller and far closer to the nucleus than the atomic orbitals of the electron. Muonic helium is created by substituting a muon for one of the electrons in helium. The muon orbits much closer to the nucleus, so muonic helium can therefore be regarded like an isotope of helium, whose nucleus consists of 2 neutrons, 2 protons, and a muon, with a single electron outside. Colloquially, it could be called helium 4.1, since the mass of the muon is slightly greater than 0.1 MeV. Chemically, muonic helium possesses an unparalleled valence electron, can bond with other atoms, and behaves more like a hydrogen atom than an inert helium atom. Muonic heavy hydrogen atoms with a negative muon may undergo nuclear fission in the process of muon-catalyzed fusion. After, the muon may leave the new atom to induce fusion in another hydrogen molecule. This process continues until the negative muon is captured by helium nucleus and cannot escape until it decays. Negative muons bound to conventional atoms can be captured through the weak force by protons in nuclei in a sort of electron capture-like process. When this happens, nuclear transmutation results. The proton becomes a neutron and a muon neutrino is emitted.